Okay, this is a larger piece of the same rock that we saw back there that I said was bedrock, but you didn't have a really good view of it. Here, it's not in place, but you get a better look at it. And it's a fine, very fine bedded limestone. This was actually a lime mud at the bottom of a shallow tropical ocean. Very much like Florida Bay today. If you go walking in shallow water in Florida Bay, you'll stir up a white or milky looking mud, and that's exactly what this rock is made of. It's a limestone, and the algae pulled the calcium carbonate out of the water, and then when the algae died, it released little tiny particles of the calcium carbonate to make up this limestone. You notice though some of the layers though are yellowish, and it stands out a little bit in relief in some places, stands up just a little bit higher. That's actually dolomite, and there's a reason why it's yellowish. Dolomite is magnesium calcium carbonate, and the yellowish is because there's a little bit of iron in it. Iron is a little bit smaller than calcium, and it fits better with magnesium than it does with calcium. So it goes into dolomite rather than limestone. Limestone will take some of it, calcite will take some of it, but it can't take very much iron. Dolomite can take more. And because the dolomite can take more, where iron is available, it goes into the dolomite, and then when it's exposed to air, it rusts. And so what you're looking at there is a goethite stain, the yellowish brown stain that we had when we powdered the goethite. This, by the way, does indicate that this was a tropical ocean at the time. Back in the early Paleozoic, Maryland not only was in the tropics, it was in the southern hemisphere tropics, a completely different part of the world. Okay, the other place I want to look at is around right here. See that rock sticking out right over there on the other side of the road? That is a fun little piece of rock, and I'll take a look though. Yeah, exactly, it's a conglomerate. And it's a conglomerate with pieces of quartzite in here, pieces of limestone. Now, over there, about a mile down the road, at the end of the graben, this is a graben, a rift valley, and there's a big fault there with several thousand feet of mountain. At one time, there was probably a 5,000 or 10,000 foot mountain range right down at the end of the road there. It's gone, it's long gone. But the rock exposed on the other side of that fault is greenstone. You'll get to see it when we drive down that way. And when that was the face of a mountain back 500 million years ago, the rocks were washing off it as a conglomerate, you know, gravel bank right at the base of the mountain slope. Here's the puzzle. Greenstone is exposed over there on the other side of the fault. Where's the greenstone? There isn't any here. So why is it then that when the fault was active over there, rocks were washing off, and yet the rocks we get like the ones from the other side of the fault? I gave you a hint there, and the hint is that there might be 10,000 feet or 2,000 or 2 miles of vertical elevation. This rock, we're right at the bottom of the basin here. These are some of the oldest rocks deposited in the basin. Most of the rocks in the basin have actually worn away. And at the time that the fault started and the first sediments came in, the rocks exposed on the other side were limestone and quartz sandstone. The greenstone wasn't even exposed then, but since then it's moved a couple of miles. The white sediments, the quartzites and the limestones, now would be 2 miles up in the air. They're long since eroded away. The only place you can still see them is in the sediments that fell down into the valley as the valley floor dropped, as the fault moved. By the time the greenstone appeared, as it was raised up even more, those rocks were deposited higher up in the sequence here in the valley, and those rocks have since worn away. So what you're looking here is when I said it was raised maybe 10,000 feet, the evidence for that is just what I told you here. The rocks being deposited here aren't the ones that are exposed on the other side of the fault now. It wasn't the same then. In geology, you have to think of 3 dimensions and also the 4th dimension of time. Not only the time since it was deposited, but the time it took for these structures and sediments to actually be deposited. It's putting together a mystery story, really. By the way, I got this when I was in graduate school in California, and we were working there also in a fault valley, making a few geology course, and rock exposed down at the lower sediments in the basin did not contain any granite pebbles with a particular fairly uncommon mineral in it. But as you went up in the sequence, you did find it. And that's because the rocks exposed on the other side of the fault changed with time as the faults moved. And so I applied that bit of information to these rocks right here. As far as I know, by the way, I have not seen this mentioned in any literature anywhere. You know, the fact that the rocks on this side and the sediments don't match the rocks on the other side. If you ever go into geology, this would make a very nice little master's thesis for somebody. Assuming it may have been written up, it may simply be that I haven't run across it yet. But anyway, for your edification, there it is. Let's go back.